Today we are going to discuss Schrodinger equation in its integral form. So we know Schrodinger equation is a linear partial differential equation that governs the wave function of a quantum mechanical system. And it is used to find the allowed energy levels of quantum mechanical systems such as atoms or transistors. The associated wave function gives the probability of finding the particle at a certain position. The solution of this equation is a wave that describes the quantum aspects of a system. So the wave function psi gives the probability of finding a particle in certain state, and the solution is the wave function. This wave function that describes all the characteristics of the quantum mechanical system. So now we are getting to our topic, Schrodinger equation as an integral equation. The Hamiltonian eigenvalue problem or time-independent Schrodinger equation is the central equation of quantum mechanics. For many problems in quantum mechanics, it proves to be useful to write Schrodinger equations in its integral form rather than as differential form. Ordinary space representation for a particle of mass m subjected to potential V of r is given by minus h cross square by 2m del square psi of r plus V of r psi of r will be E psi of r. That is, in ordinary space representation, Schrodinger equation is represented by equation 1. So this is a partial differential equation. Here psi is the wave function, is the energy of the state described by the wave function. V is the potential energy, m is the mass of the particle, and h is the scaled Planck's constant. Now we have to find the momentum equivalent of this equation, that is equation 1. So we multiply equation 1 with 2m by h cross square. So we will get minus del square psi plus 2m by h cross square V of r psi of r is equal to 2m by h cross square E psi of r. 2m by h cross square, this term is taken to left and this will be taken to right side. Here it will be positive, no minus. And let 2m by h cross square E of r, this term be a square and this term be u of r. So we will get equation 2. Now if V of r comma r dash is equal to V of r dash into delta r minus r dash is a special case where delta will be delta function will exist for r equal to r dash, then equation 2 will become del square plus a square psi of r integral V of r comma r dash psi of r dash d cube r dash, where d cube will be the volume. So we get equation 3. Now consider the Fourier transform pair. Psi of k is equal to 1 by 2 pi raised to 3 by 2 integral psi of r e raised to minus psi k dot r d cube r. That is equation 4 will be the Fourier transform of psi of r. And we have the inverse transform given by equation 5. Now multiply this with e raised to minus k I k dot r and integrate with respect to d cube r, that is the volume. So we will reach the equation 6. Now we have to separately integrate both the sides. So integrating LHS, we have LHS integral del square plus a square psi of r e raised to minus I k dot r d cube r. Let delta equal to ik, then del square will be let del be ik, then del square will be minus k square. Then we will get equation 7. Similarly, we integrate RHS substituting equation 5 here and integrating, we will get equation 8. This will be equation 8. This will be equation 8. After that, we can equate LHS and RHS. We will reach to this equation. We will reach to this equation, that is minus k square plus a square psi of k will be equal to this. Let this whole term be f of k dot k comma k dash. Then we can write this one as minus k square plus a square psi of k integral f of k dash psi of k dash d cube k dash. And this is the momentum representation of the Schrodinger equation. That is the integral equation. Now let's consider